All right, in this video we're going to talk about sequences, which will lead up to the next one where we'll talk about series. So I'm just going to kind of throw out, maybe not a bunch of definitions, but exactly what a sequence is, whether it converges or diverges. And a lot of these definitions are just important for what is coming up in terms of studying series. So a sequence, it's just a list of terms. And it's a list of terms. We usually call these A sub n, and they are defined by a function. So defined by a function, but defined by a function in terms of n. We usually use n. N is the index, and n is usually equal to like 0, 1, 2, etc. It's usually whole numbers. Sometimes it starts at 1, sometimes it starts at 100, but in general, when we think of n, we just think of whole numbers. So some notation. So notation here, and maybe I'll give an example too. So we could say that A sub n is equal to, let's just say 1 over n. And so another way that we could notate this is we could put it into curly brackets. So we could put A sub n in curly brackets. We could put 1 over n in curly brackets, or we could list all the terms out in curly brackets. So if we listed all the terms out, and let's say that this one, well, we can't start at 0, so let's say this one starts at 1. So the first term is when I plug in n equals 1 into this term, so 1 over 1 is just 1. The next term is plugging in n equals 2, so that would be 1/2. The next term is plugging in n equals 3, that would be 1/3. The next one is plugging in n equals 4, that would be 1/4, and that continues. So this first one was plugging in n equals 1. The second one was plugging in n equals 2. The third one was plugging in n equals 3. And the fourth one was plugging in n equals 4. So those are 4 terms in this sequence. It's just a list of numbers. It was defined by the function 1 over n, and we started when n was equal to 1. So there's an example of one sequence. Here's another example. Let's look at the sequence -1, 4, -9, 16, etc. And for this one, let's write out the A sub nth term in it. So what we have to do is kind of look at the pattern here and figure out the function, figure out what the pattern is doing. Now, first of all, it's got a minus, plus, minus, plus, minus, plus. We can usually do that with a -1 to the n. Now, if it starts negative, it would have to start at n equals 1, because if I plug in n equals 1, that gives me -1. If I plug in 2, it gives me positive, which would give me a positive value in front of that. N equals 3, I'd get a negative. 4 is positive, so I'd get a positive. All right, so that -1 to the n takes care of the negative, positive, negative, positive. Now we've got to look at the numbers. Now it starts at 1. 1 would be the same as 1, so maybe it's n. But then that wouldn't work at n equals 2 because that's different. So if you kind of look at the pattern here, maybe you can notice that this 1 would be 1 squared, 4 would be 2 squared, 9 would be 3 squared, 16 would be 4 squared. And so if we do n squared there, and then I like to check it, so we're starting at 1. So if I plug in 1, I get -1. There it is. If I plug in 2, I get positive 4. If I plug in 3, I get -3 squared is 9, -9. I think I've got it. All right, so the sequence here, or the function defining that sequence, is -1 to the n, n squared, and it is important that we say where it starts. this domain of the sequence that really is important and kind of part of listing out a sequence. Okay, so there's some examples of sequences. Now let's look at convergence and divergence. So we say that a sequence converges. A sequence converges if the limit as n goes to infinity of a sub n is equal to some number. If we get, this isn't very mathematically, notationally correct, but that's okay. If it's equal to some number. So the sequence converges if you take the limit of that function that defines it, and you get a number. Otherwise it diverges. Diverges. So it's going to diverge if the limit as n approaches infinity of the a sub n is either equal to plus or minus infinity, or if it does not exist. So in either of those cases, the sequence diverges. So just like when we worked with integrals with limits in them, if we got a number, we said that it converged, and it's the same concept here. If we take a limit, we say that it converges. And so let's look at a pretty simple example here. Let's just look at a sub n equal to 1 over n, where n is greater than or equal to 1. And if we take the limit as n approaches infinity of 1 over n, we would get 1 over something really big, and that's 0. We get a number, and it converges. And here's kind of a picture of that, just so you can get a picture in your head of what this is doing. So if let's say this is like the n-axis, and we treat this as a function of n, when n is equal to 1, we get 1. When n is equal to 2, we get 1/2. When n is equal to 3, we get 1/3. When n is equal to 4, we get 1/4. Then 1/5, and then 1/6. And you can kind of see how all of those dots eventually go to 0. All right, so let's look at another few examples of convergence and divergence. So let's just do the following. Converge or diverge. Let's look at, first of all, the sequence. Let's look at 3n squared plus n plus 2 all over 2n squared minus 3. Let's take a limit as n goes to infinity of 3n squared plus n plus 2 all over 2n squared minus 3. Now, it's going to be nice to have some shortcuts on this. And notice that if you plug in n equals infinity, you get infinity on the top, you get infinity on the bottom, you get infinity over infinity, and you should apply L'Hopital's rule. So you would take the derivative of the top, the derivative of the bottom, and you would have to do this twice before you'd, maybe 3 times, before you would actually get a number out of it. Now, because the powers are the same, so here's your key. It goes to infinity, the powers are the same, and because the powers are the same, we can just pick the numbers that are out in front of the highest power. This limit is going to equal 3/2. Now you can try it, you can do L'Hopital's a couple times, and you'll see how you will get 3/2 at the end of this. But because those powers are the same, when you take the derivative, they reach a number at the same time, the same number of derivatives. And so you end up getting 3/2. So the rule is, if the limit is going to infinity and your powers are the same, you can look at the numbers in front of your powers. It's a nice shortcut. All right, so this one converges. This sequence converges and we get 3 halves. Let's do another one. Let's look at n cubed plus 2 all over n squared plus 4n. If we take a limit as n goes to infinity on this one. Now notice on these ones that the powers are not the same. There is a bigger power in the denominator. So, or I'm sorry, in the numerator. The numerator is bigger. And so the limit as n cubed plus 2 over n squared plus 4, the limit of that as n goes to infinity is going to be infinity. And that's because the top is bigger. And so this one would diverge. Now, what about n plus 2 over n squared plus 4n? Notice on this one that the power in the bottom is bigger. And if the power in the bottom is bigger, you can think of this limit as a 1 over infinity. So we're going to take the limit as n approaches infinity of n plus 2 over n squared plus 4n. The bottom is bigger. If the bottom is bigger, we've got essentially, I think of that as like 1 over infinity, which would go to 0. So this would converge to 0. I forgot to box this upper one. Okay. All right. Let's see. Let's do another one. Let's look at when a sub n is equal to n factorial over n plus 2 factorial. When we take a limit as n approaches infinity, remember that n factorial is n times n minus 1 times n minus 2, and that continues until you hit 3 times 2 times 1. So that's expanding out n factorial. I'm going to do the same thing with n plus 2. It's n plus 2. I subtract 1 from that, that's n plus 1. I subtract 1 from that, and that's n. Subtract 1 from that, and that's n minus 1. And that would continue until we hit 3 times 2 times 1. And then notice that a bunch of stuff is going to cancel out of this. We're going to get all of those n's all the way to 3, 2, 1 in the top to cancel. And the same thing is going to happen in the denominator. What we're left with is something very big in the denominator. So essentially we have 1 over n plus 2 and n plus 1. The power in the denominator is bigger. This goes to 0. It's going to converge. All right, and let's look at one more. Let's look at if a sub n is equal to 5 halves to the n. If we take a limit as n approaches infinity of 5 halves raised to the n, to the n, this is the same thing as 5 halves is 2.5. And if we take a whole number and then keep raising it to bigger and bigger exponents, it's going to get really, really big. And so this guy diverges because we get infinity. So if this had been, okay, one more, I was joking. If this had been 2/5 n, then that limit of 2/5 n, because 2/5 is less than 1, because it is a decimal less than 1, when you raise it to an n, it essentially gets smaller and smaller every time. This one goes to 0. So the difference on these two is that this one had a number bigger than 1 raised to an n, and that diverged. This one had a number smaller than 1, and so it converged. All right, and these last two type of sequence called a geometric sequence. Geometric sequence. And a geometric sequence in general looks like a sub n's equal to c times r to the n, where c and r are just, they're some numbers. And in general, if we take the limit as n approaches infinity of cr to the n, we are going to get, we're going to get 0. We're going to get 0 if r is in between 0 and 1. So if it's equal to 0 and you take a limit of that, you just get 0. And we just saw on the last example that if r is a fraction that's less than 1, it goes to 0. Now, if r is equal to 1, 1 raised to anything is 1. And so the limit is just, we'll just get c out of that. And then that, in the last example, maybe not the last example, the second to the last example, where r was bigger than 1, we saw that it went to infinity, that limit, and so it diverged. All right, so these are just a special kind of a sequence where you have a number raised to an nth power in your function. All right, there is another special kind of a sequence that's defined recursively. So a recursive sequence where the next term is defined by the previous term. So the next one in line depends on the one behind it. Here's an example. Let's say that a sub n plus 1 is equal to a sub n over n plus 1, and let's give a starting point. Let's say that a naught is equal to 1. All right, so we're starting at a naught equals 1, and I'm going to plug in n equals 0. Now the reason I'm plugging in n equals 0, if you look at this, if I plug in 0, my next term is a sub 1. It's the next one in line. Now plugging in n equals 0 into all of this, I get a1 is going to equal a0 divided by 0 plus 1 is 1. And a naught was defined before this. It's 1. So I get 1. Then I plug in n equals 1. When I plug in n equals 1, I get a sub 1 plus 1. That's a sub 2. That's the next one. That's going to equal a sub n, and in this case right now is 1, so a sub 1 divided by 1 plus 1, which is 2. A sub 1, we just found that to be 1 in the previous step, and so a sub 2 is 1/2. When n is equal to 2. So now I'm going to plug 2 into all of these n's. So I get a sub 3, because 2 plus 1 is 3. A sub 2 divided by 2 plus 1, that's 3. A sub 2 was 1/2 times 1/3, so a sub 3 is 1/6. Let's do one more. N equals 3. This is going to give me a sub 4. So right now I'm plugging in 3 into all of this. So a sub 4, a sub 3, 3 plus 1 would be 4. So on the top, a sub, what are we plugging in again? 3, there we go. Divided by 3 plus 1, which is 4. A sub 3 we just found in the previous step is 1/6. Multiply that by 1/4, and we get 1/24. Right, so we still get a list of numbers. Our list of numbers is 1, 1, 1/2, 1/6, 1/24, and then this would continue forever. It's just done so that it's in terms of the function beforehand. So we've got sequences that are just defined by functions with just n in them, and then recursive sequences which are defined by terms that come before. All right. So let's see. One other thing we need to talk about is if sequences are increasing or decreasing. Increasing or decreasing. So if a sequence is increasing, then the next term is bigger. Next term is bigger. If sequences are decreasing, then the next term is smaller. I think that's pretty intuitive. So if we look at, let's look at a few examples here. Some of them are kind of obvious. If you look at just a sub n equal to n, well, that's the sequence. Let's start at 0. So that's the sequence 0, 1, 2, etc. Even just in the first few, it's pretty obvious that the next term is bigger, and so this sequence is going to be increasing. We can also show this in general by saying that the next term, that's the n plus 1. So the next one is n plus 1. That term is bigger than the one before it. So this is the next term is bigger than the previous term. Next term is bigger. All right, I'm just stating that. All right, sorry for that little blip. It probably put up a blank screen and then is coming back to here, but I didn't mean to push that button. All right. Okay, so we're talking about increasing or decreasing, and here's a pretty easy sequence that increases. If we look at a sub n equals 1 over n, this is the one that we graphed before. So this is the sequence. Let's start this one at 1. 1, 1/2, 1/3, 1/4, etc. Now this one, each term is getting smaller, so this one's decreasing. Decreasing. So, and we could show this in general, because we could say that the next term, there's the next term, it's the one where I plug in n plus 1 in for n. That next term is smaller than the one before it, because if I have a bigger denominator, the whole thing is smaller. Right, so there's an increasing sequence, there's an obvious decreasing sequence, and let's look at one more that's kind of not so obvious. Let's look at what if a sub n is n plus 1 over n. So now we've got part of this, which is, we know that n is increasing, we know that 1 over n is decreasing, and I don't really know whether this is actually increasing or decreasing in general. So what I'm going to do is just sort of, I'm going to make a guess. Right, so I'm going to say that, put that there. I'm going to say that n plus 1 over n, I'm just going to say that maybe, I don't really know, maybe this is smaller than n plus 1 over n plus 1. So I'm saying the next term, so I plugged in n plus 1 and n plus 1, and for n, the next term is bigger. So I'm saying this is increasing. I'm saying that the next term is bigger so that it'll be increasing. And there's a big question mark there. I don't really know for sure. But I'm going to just kind of do some algebra to this and then see what happens. So first of all, I'm going to cancel those n's. They're on both sides. I could just subtract them. And then I am going to subtract the 1 over n plus 1 over to this other side. So now if I combine this as a fraction, I get n plus 1 minus n all over n times n plus 1. This is still kind of a question mark in here. So I get 1 over n times n plus 1 is less than 1. So I've just kind of kept on going with some algebra in here. I'm just kind of moving some stuff around until I can see whether this is true or not. At this point, there is something bigger in the denominator than 1. And so that whole thing has to be smaller. Bigger in the denominator, whole thing smaller. And so I can check that inequality is actually true at this point. And so what I assumed to begin with was true. So this one is increasing. So this one is increasing. Now, if we'd done all this work and then found it not to be true, if we found that we could just flip that inequality, well, then it would have been decreasing. So I just sort of make a guess, and I do some algebra, and then see if it's true or not. All right, so that was just a few different, kind of an introduction to what a sequence is. It's a list of terms, whether it converges or not. We looked at geometric sequences, and then we looked at whether a sequence was increasing or decreasing. And the next video, we will now start looking at series. Oops, I didn't mean to do that. Can I undo that?